All right, if you would go and take your homework handouts, and we completed the first box, which was 3 problems. We completed the first part of the second box, where we were finding the work done by a wall that ricochets off of the wall. Let's go ahead and take a look at the second part here of that second box. And Michael, if you'll read that for us.
Another 185-gram softball is hit at 32 meters per second into the pitcher's glove. Assuming the glove stops the ball, determine the work done by the glove.
Again, how do I find work, class? There's a few different ways. Okay, force times displacement. Obviously, that's no help here because we don't know a force or a displacement. Change in kinetic energy. That's if the mass or velocity, usually the velocity of an object, is changed. That's what we're going to use here. The other way is
potential energy.
Change in potential energy. Now, it would be if the height of an object has been changed. All right, we're going to lock in on this one here. Change in kinetic energy means we have some initial kinetic energy, we have some final. Change is always what minus what, class? Final minus initial. And kinetic energy in general is 1/2 mv squared. So we're going to take 1/2 mv sub f squared minus 1/2 mv sub I squared. Now, initially it says the ball is hit at
32 meters.
So that was the ball's initial velocity, 32 meters per second. That's got to be squared times the mass of 0.185 kilograms, 185 grams. Take half. Subtract that away from what it ends up at. What does it end up going? 0. And so if the velocity is 0, it ends up with 0 kinetic energy in the final sense. So we'll take just the negative, if you will, of this, which means the work we get is going to be negative because it stopped the ball, right? The ball had energy. The glove took all that energy away by stopping the ball. All right, and so literally all you got to do is multiply these numbers together, square the 32 times 1.85, take half, don't forget the negative. What did you get for your answer, Michael?
I got negative 189 joules.
Kendall?
I got negative 17.5.
Ooh.
Negative 94.7.
That's what I had, negative 94.7 joules. What did you say your answer was again, Michael?
189.
I think you forgot the half.
Yeah, probably.
Kendall, what did you say your answer was?
17.5.
I was about to say, I think you forgot to multiply by 32, but that can't be it either. Go and plug it in again to your calculator, make sure you're good to go there. Now remember, this kind of emphasizes the point I was making when the first ball hit the wall. The glove stopped it. It did a bunch of negative work to stop it. The wall also stopped the ball, right? When it ricocheted, it hits wall and ricochets. Well, it stopped the forward progress. That's work, negative work. And then forcing the ball the other way on the ricochet, that's more negative work being done. So on any time there's a ricochet involved, that's increasing the amount of work. It takes work to stop. It takes more work to produce the ricochet. Okay. Questions on that second box? All right, let's go to the third box now and read that first problem for us, if you would, Kendall.
A spring is stretched 7.53 centimeters. If the spring constant is 375 newtons per meter, how much potential energy is stored in the spring?
All right, so it's a very strong spring, stretched not that much, about that much or so. So not a lot of stretch there. Finding the potential energy. Again, which one's going to affect the potential energy more, class? The strength of the spring or the amount of stretch? The amount of stretch has the greater impact here, and we're going to see that because it's not a whole lot of energy. What equation did we need to use for elastic potential energy or spring potential energy, class?
P sub S equals 1/2 kx squared.
All right, thank you, Michael. Ladies, did you have that equation? P sub S equals 1/2 kx squared. All right, you can't use MGH, right? Because what gravity and what height, right? So 1/2 kx squared for spring potential energy. We haven't used this equation a lot, so glad we were able to work it into the review here for you. We're simply going to take half of the spring constant, which is 375 newtons per meter. We do have to change the stretch, though, to what? 0.0753, so it's meters, and square it. And what do we get for the potential energy stored in the spring, Michael?
I got 1.06 joules.
When you round off, 1.06 joules is correct. All right, so ladies entering it there. Big thing is make sure you know the equation. All right, that's the biggest thing on that. All right, here we go. A ricochet. A ball is pitched and then it's hit, so the ball is changing direction. Let's take a look. Read this second problem in box 3 for us, Audrey.
145 gram baseball is pitched with a velocity of 36 meters per second. The batter hits the ball to give it a velocity of 47 meters per second out to center field. Determine A, the impulse of the hit, and B, the force applied if the bat made contact with the ball for 0.034 seconds.
All right. It asks for the impulse. What letter did we use to represent impulse, class?
J.
J. That was from our last lesson, remember? And we said there's actually two ways you can find impulse. It's literally defined as the product of two things, class.
Force times.
Force times time. But we said we could also think of impulse as a change in momentum, which could be represented delta P, or the way I like to represent it,
M delta V.
M delta V, right? That's actually what change in momentum is. So either one of these two equations could be used to find the impulse. Well, the first number I'm given, class, is a mass, and the next two numbers I'm given are velocities. So which of these two equations should I use to find impulse? FT or M delta V?
Delta V.
M delta V. So we're going to go with this one. I'm going to change the 145 grams, of course, to
145.
kilograms. Now think about the change in velocity. Remember, this is final minus initial, correct? Initially, how fast was the ball going?
36.
36. But it was hit at a speed of
47.
the other direction because it went out to center field, right? If the pitch goes in toward the plate and the hit goes toward center field, the hit's in the opposite direction, correct? So I'm not going to write 47 for the final velocity. What's the final velocity? Negative 47. So what is the change in velocity here, class? Negative 83 meters per second. Remember, if all you want to do is stop the ball, you could catch it, and that would change the velocity 36. But to turn around and send the ball out towards center field an additional 47 meters per second means your total change is 83. Now, if you thought of the pitch as being negative, and you thought of the hit as being positive, from the batter's perspective, right? As a batter, as the ball's coming toward me, that's negative, that's positive. In which case you'd say positive 47 minus negative 36, and then you'd have a positive 83 right here. From a pitcher's point of view, which is what I do in PE class, pitching toward the plate is the good thing, and the ball being hit back at my face is a bad thing, right? So this is from a pitcher's point of view negative, batter's point of view, you'd think a positive 83. Really doesn't matter, just impulse will be determined by the perspective of who we're looking at here. We're just going to multiply the 83 by the 0.145. What do we get for the impulse?
Negative 12.035.
And is it 3 sig figs, 2 sig figs? 2 sig figs.
Negative 12.
Negative 12. And what are we going to use for impulse? There's actually two different units we could use.
Newtons times seconds.
Newtons times seconds would be the force times time equivalent. No problem using it here. If we wanted to go more natural, we had kilograms times meters per second. We could use that as well for impulse. Again, if you had a positive 12, that's actually okay, because that just means you were looking from the batter's perspective. So I will take either positive or negative 12 newtons times seconds or kilograms times meter per second squared. Did anyone have that for the impulse? All right, does it make sense now? Again, you can't say 47 minus 36 is a change of 9, because the pitch coming in didn't change speeds by 9 miles an hour, did it? It completely stopped. That's a change of 36. And then it also went that way. That's an additional 47 and change. Does that make sense? All right. But we're not done with the problem, because now it says find the force applied if the bat made contact with the ball for 0.034 seconds. Well, that's kind of saying that force times time is going to equal this. So that means the force times the 0.034 seconds of contact time equals the negative 12.03 blah, blah, blah. Not negative 12. The unrounded value that's hopefully still on your calculator, newtons times seconds. To get the force, class, I would have to divide away the 0.034 seconds. And again, if you're thinking of it from the pitcher's point of view, which is how we drew it up, the force is negative because the force is aimed against or at the pitcher. And so what is the force that the bat must have applied to that ball? Negative 353.97, or rounded off, we'll say negative 350 newtons of force. Again, from the batter's point of view, positive 350 newtons of force, because you would have had a positive impulse. Questions on that box? All right. Go and read the next box, and it's just one problem in this box now. Michael?
A 780 kilogram car going 20 meters per second is rear-ended by a 580 kilogram car that was traveling at 22.5 meters per second. If the final velocity of the first car is 22 meters per second, determine the final velocity of the second car.
All right, I actually gave you the equation here only because it was easier to do that than list all the little, well, let's assume that no brakes were not applied, let's assume there's no friction, blah, blah, blah. We're just going to assume no outside forces, which is really unlikely, that no brakes, no friction, no whatever. Let's assume no outside forces, in which case, class, this, what kind of collision would this be?
Elastic.
Would it be elastic, inelastic, or completely inelastic?
Completely inelastic.
Did the two cars crunch together and stick together? It didn't say it did. I mean, maybe it did in the rear end collision, but it didn't say they stuck together. Inelastic, right? We can't say elastic because elastic would be there's no damage to either vehicle, there's no sound given off, there's no, definitely not an elastic collision because kinetic energy would also have to be conserved. That's not going to be the case, but we'll assume momentum's conserved, right? So this is where we went with the MAVA plus MBVB equals the MAVA prime, MBVB prime. We just had to plug in the numbers. So the first car's mass, Michael, you said was?
That is 780 kilograms.
Kilograms, and it was going at?
20 meters per second.
20 meters per second. Second car's mass?
580 kilograms.
Smaller vehicle. How fast was it going?
22.5.
22. Who hit who, by the way?
The smaller car.
The smaller car rear-ended the bigger car. So you got a big car going down the road. A little car's going faster. That's when I heard the 22. The little car's going faster, and it bumps the other one. Now, if it's a rear-end collision, that means the cars must have been going opposite direction or same direction? Same direction to rear end. So both of these velocities will be positive. All right? Then after the bump, 780 car, is that what we were finding, or did we know how fast the 780 car was going after the bump?
We know how fast it was going.
Okay, so 780 car gets bumped, and that jolts it forward a little bit, causing whiplash, but that's not in the problem. So what speed did the larger vehicle take on?
22 meters.
When it got bumped at the 22 meters per second, it sped up to 22 meters per second. Now, practically speaking, if the smaller car bumps the first one, again, no brakes applied, what should happen to the second car? Do you think it will ricochet off? Or do you think it'll slow down? Do you think it'll keep going at the same speed, it'll keep going together? What do you think would happen? I don't think it'll bounce off, but I do think it'll slow down. It'll still be going forward, it's just that bump, and the first car gets moving a little faster, and the second car probably gets slowed down. So I'm expecting that the 580 kilogram vehicle has a lower velocity than 22 that it used to have. All right, so we get to do a lot of math, and do the 780 times 20, and that's 15,600. 580 times 22, and that's another 12,760, which is 28,360 on this side. 780 by 22 is a 17,160. Of course, that's a 580 V sub B prime. Let's knock the 1760 out by adding it to the negative to the 28,360. 11,200 equals 580 V sub B prime. When you divide by the 580, how fast is the little car going after it bumps? Anyone?
19.8.
I have 19.31. Ooh, I might have mistyped something then, because I have 19.81 on my paper.
Oh, a 22.5. Right there.
I said 0.5.
Oh, did you? Why didn't you tell me I didn't write 0.5? Let's go with 22.5. So that's going to change this number, which is going to change this number, which is going to change this number. 19.81 is the answer Michael got. I'm too lazy to rewrite it up there. Hopefully you have 19.8 by the time you get 3 sig figs. 19.8 meters per second. Slows it down a little bit after it bumps the bigger car. Questions on this? All right, want to read the last one for, have you, Calvin and Hobbes? Yes, no, yes. Okay, good. You're a good choice to read this.
Calvin and Hobbes are having a snowball fight. Calvin misses Hobbes with a snowball, and he gets to run away from Hobbes at 7.5 meters per second. Hobbes throws a 0.95 kilogram snowball at 24 meters per second. It hits Calvin in the back of the head and sticks to him. Find Calvin's new velocity if he weighs 280 kilograms.
All right, I gave you the equation here, and the key phrase, you should have known which equation to use even if I hadn't given it to you, because of what 3 words, class? Sticks to him. That tells you we're dealing with a completely inelastic collision. So we've got whatever mass Calvin has in his velocity, we've got whatever mass, not Hobbs, but the snowball has, and its velocity is going to be equal to the combined masses of Calvin and snowball times the final velocity of same. All right, so let's see. Let's start with Calvin. Does it give us Calvin's mass? What does it give us, class?
Wait.
That Kendall, that look on her face of, they did it to me again. Gotta divide the gravity out. What is Calvin's mass? This would be a good thing to put in the memory, by the way, if you didn't have it.
28.57.
Yeah, 28.571, good number to have in the memory. And he was running at a speed of
7.5.
7.5 meters per second. The snowball is thrown. It has a mass of
0.95.
Okay, and that's actually correct. And its velocity was
24.
positive or negative, class? Hits him in the back of the head.
Positive.
Going the same direction, it is a positive 24. Good. If it hit him in the face, we would assume it's negative 24, right? So should this snowball speed up Calvin or slow down Calvin? He's running along, whoop, what should happen? Assuming it doesn't knock him down. At least momentarily it should speed him up, right? Even if it does knock him down, it speeds his head up at least, the part of him that gets hit. So we'll take the combined mass, which is this plus 0.95, whatever that is. It's, I don't know, like 29.551, blah, 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 something like that. Times final velocity, multiply, add them together, divide by that. What do we get for the final velocity? Anyone set it up correctly? Hopefully. Can I call out your answer?
9.248.
That's not what I had. I had 8.0. Go and re-enter it. 8.03, blah, blah, blah. And it's a 2 sig fix. So yeah, 8.0 meters per second. He was going 7.5 meters per second. It sped him up another 0.5 meter per second when he got honked in the back of the head by said snowball. Questions on this? All right. Go ahead and clear your desk at this time, except for a clean sheet of paper and a pencil and a calculator. Clean sheet of paper, pencil, calculator, everything else away. First lesson name at the top of your paper, along with today's date, which is 12/16/22. 12/16/22, today's date. First and last name, 12/16/22. And this is quiz 15. It'll be your final quiz of the semester. Quiz 15. I'm going to go over the quiz instructions with you, and then if you're watching on YouTube, I need you to pause the video once we begin the quiz. Once you're finished taking the quiz, go ahead and resume the video, and we will begin our exam review. All right, let's take a look at the quiz together very quickly here. First 10 questions are completion. Write the word or words that would best complete each statement. Some answers may require more than one word. Problem solving. Numbers 11 and 12, straightforward. Number 12, or 13, excuse me, refers back to number 12. Number 14, 15, straightforward. And then in number 15, the bonus builds on 15. So using the information, so once you get 15, make sure you keep whatever memory values you may have found. You'll want those for the bonus. All right, so for those watching on YouTube, take just a moment and pause the video while you work. Once you're finished, go and resume, and we will begin our exam review. All right, I trust you did well on that quiz. If you would, go ahead and take out some notes to where we can review over some of these things that you will need for your exam. Obviously, terms will cover the entire semester, so chapters 1 through 12. The math, however, will primarily be the last few chapters. Chapters 10, 11, and 12. So more recent math is what you can expect to see here. Want to quickly go over some equations, key equations you'll need for the exam. One of the things we talked about in chapter 10 was uniform circular motion, centripetal force. And remember that centripetal force equation? Call it if you do.
MV squared over R.
MV squared over R. Write that in your review notes. Good. What about work? Now, we've got actually several equations for work. We reviewed them earlier this hour, class.
F times D.
Good. Any and all of those would work. Of course, we also have an equation for power. 3 equations, in fact, for power.
FD over T.
Which, since work is FD,
W over T.
which is actually the definition of power, right? Work per unit time. There was a last one. Said since distance over time is, or displacement over time is velocity, I'm going to force times velocity. So a few different equations for power. Kinetic energy, obviously getting now into chapter 12. This from chapter 10, chapter 11, chapter 12 equations. Kinetic energy, just used this on the quiz a moment ago. 1/2 mv squared. Potential energy, used this on the quiz a moment ago also.
KX.
Well, if it's spring potential energy, yes, 1/2 kx squared, but regular potential energy we normally think of as gravitational potential energy, and I probably should have specified that.
MGH.
MGH. And impulse. Again, this was used at the last problem of the quiz and then also on that bonus problem as well. 2-part equation.
F times T. M times delta V.
There we go. So these are the equations that you will need to be able to use, to know and use on your exam, as well as the law of levers. Now that's not a letter I put up there, but what was that law of levers equation that we talked about in the chapter where we dealt with work and power there in chapter 11? What was that law of levers?
So
R sub I equals F sub O, R sub O.
Yeah, phi re equals pho rho is one of my students used to like to say. There we go, good. And then of course the conservation, momentum, excuse me, the momentum equation.
P equals MV.
And so conservation of momentum is simply mv plus mv equals mv prime plus mv prime. We just using a little a's and b's and a's and b's to indicate that. All right, these are the equations you will need for your semester exam, so make sure you get these jotted down. Take good note of those. One last thing I want to review with you very quickly. I know bell's about to ring, but wanted to go over units. I'm just going to call them out as opposed to writing them down. SI units for mass. Kilogram, time,
Second.
length,
Meter.
velocity,
Meters per second.
meters per second, acceleration,
Meters per second squared.
meters per second squared, force,
Newtons.
pressure. We haven't done that one in a little while.
Pascals.
Pascals, very good. Atmospheric pressure, we had torrs and ATMs as well, but normally pressure measured in pascals. Work, joules, power, watts, and watts. Frequency, hertz, period.
Second.
Seconds, because it was a measure of time. Energy, both kinetic and potential.
Joules.
Joules, momentum.
Kilograms times meters per second.
Kilograms times meters per second. Impulse. Newtons times seconds, or kilograms times meters per second. All right, we're going to be going over this quiz in our next lesson. At the start of the lesson, obviously that will not be on YouTube. We'll do some terms review as well in our next lesson. And then for homework in the next lesson, we're going to be giving you some more math work specific for the exam. Lesson 89 will be our math review, and then lesson 90 will be the exam, and you'll have finished your first semester of high school physics. All right, have a wonderful rest of your day, and you are dismissed.